All right, CE495. Let's move on to 3D model. I think first of all, I like to just talk about that the total 40-story building and their gravity load takedown. So if you have those model, you copy it. Basically, your model is ready to just for column design, right? So basically, we're gonna just check the all actual force diagram under the dead load. And make sure your column, you see that red color means the compression forces, which all the column reaction is cumulative, go all the way down. It's cumulative. So you see that this model doing the great job and take all the gravity forces. So just make sure when you run the model, always better double check. And this model, I have construction dialog, which I'm not going to use it for column and beam design. This is only just for composite floor framing beam design. So most likely we're going to use dead load, which is self-fed, and spawn post dead load and live rod, right? So similar to excuse me, the composite floor framing design, we're going to set up the load combination for the column design. So in the load combination menu, go to add default design combinations, and we're going to click the steel framing design instead of composite beam design. Basically very similar, but I think setting we need to follow. So when you click it, you see that you develop the all strengths load combination, which is 1.4, 1.2, 1.2 dead load, and 1.6 live load, which for column is currently is composite beam only, the gravity frame column, which meant to be take only gravity forces, which is actual, not lateral. None of the column and beams are contributing in the lateral system because we have all the beams moment released, right? So we most likely use S1 and S2 load combination for our column design. So let me, again, you can just double check your moment release to see that all the beams are sure connected, right? Moment release. This is simply connected to the column. So what we're gonna do, we're gonna just select all the column because we don't try to size the column based on using the auto selection property. Let's check the property for our column. Yes, I think we're using a lateral column auto select the property so that the tab's gonna choose the applicable column. So because this is being model, maybe we're gonna just either turn off all the element except the column or select only column, right? Maybe select show selected object only member. So I'm gonna select and go to design, steel frame design. Better, so let's check and select the group. I think we're gonna design all the column here, right? So we're gonna choose the column and then go to design again, and we select the load combinations, which most likely this is gravity column, so we're gonna use S1 and S2. So go back to steel frame and then I'm gonna start design. What's going on here? Optimizing steel auto select practice. Oh, there's some. Okay, so here I just only show all the column. Maybe you could just again you could show all. Probably either you could turn off the all others and opening. Yeah, so this is all the columns. So you can select and go to design, steel framing. Since you wanna, because you wanna size the all piece, each member. So I'm gonna just leave it like that. I don't wanna group yet. So go to select the load combinations. See S1, S2, gravity load combination. I'm gonna start design. So ETAP's gonna choose the appropriate column size based upon all their gravity column loads, actually especially axial force based upon 1.4 dead load or 1.2 dead plus 1.6 live load. Since we are selecting using auto selections, we need to go back and just to verify all members and say OK and read on it. So override auto select member size will be overridden by the member that ETAPS just designed. So this is just saying similar procedures, same as the composite beam framing. We just complete the columns. Obviously, in reality, as I mentioned, that every two floor, we're gonna have the same size. I'm gonna turn on the section and see the member size is maintained. Oh, 14 by 342. Here, 311. 283. So you see that sizes gradually reduce. Alright, so at this point, we just complete the column design. I'm gonna turn up the member size. You guys actually run and also complete the column. Gonna turn on for this bit, turn on the all. So what we're gonna do is now we're gonna, since we already set up the wind load, gonna define load patterns. Here wind X and wind Y. As you know, this is we have ultimate wind pressure, right? But for deflection check, we're using service wind load. So what we can do is we just use this as a reference, the wind forces, but we maybe we're gonna create the load factor, which is 1 divided by 1.6, so which is 0.625 wind X. So this is service wind. We're gonna use it for our deflection check. Wind X service, right? So I'm gonna choose wind X, but at that time 1 divided by 1.6, right? So this is our wind load, which is scaled down to the service level. Okay, I'm gonna copy again and I choose to Y direction. Okay, so this is wind X and wind Y. So since I add the wind load combination, I'm gonna just change to plan view, and I'm gonna put out the wind deflection plot. And can I get, okay, I can get the wind X load diagram, right? So this is our deflection, which this model has a strong axis in X direction. Deflection under the wind X, service wind, I think we have a 4.19 inches deflection, but Y direction, let's check, 26 inches. So we have a very, we need actually, we have a lack of the stiffness in Y direction. You can already see it. The building is rectangular, so the wind pressure on Y-axis is bigger because the tributary width is bigger than X, right? Also, your core wall, when you look at this, the concrete tube, when blowing Y direction, as I associate our core wall tube, weak axis shows the lateral stiffness. So that's why we end up with big deflections. You could just maybe play around the deformation shape. Y direction is governing. So we need to somehow size the wall, our backbone, to meet these deflections. So we can just look at the elevation, which may be graphically more clear. So let's choose the one elevation view 3 in the wind X, wind Y deflections. Oh, wait a minute, this is not the right, so there might be, okay. So this is the transverse short direction. You see the deflection is almost 40 to, oh, this is wind, let's see, service wind load. Oh, yeah, service X and service Y. So we're gonna have a 26.3 inches. So all right, so we have the initial study based upon just pure concrete wall. I think its default is 12 inches. Now let's see how to organize your data, right? So you probably can just for now use your wind. Mostly currently you need to pay attention and the wind Y deflection is extremely too high, which our case, our design criteria at the 40th story, we try to meet the deflections H over 400, let's say H over 400, which is 600 feet divided by 400, 600 times 12 divided by 400. So our limit is 18 inches, but we have 26 inches. So we need to somehow increase our concrete core wall as a backbone, right? So you can see that there are many ways you could pull it out the data. I'm gonna pull it out. Click this Excel, format it. So you see that all the deflections in the Y direction. I'm gonna select and copy, and I'm gonna put it here. So this is, let's say, deflection in Y, right? In inches. So we're gonna just continuously increase our stiffness, wall thickness, and then we'll continuously iterate and by increasing the wall thickness and also increase the concrete strength, so that we're gonna find out the reasonable wall thickness to meet our HO 400. We maybe want maybe stop or limit our wall thickness as maybe some 24, 26 inches, because you don't want to continue to keep increase the wall thickness, because we're losing some leasable space, or continuously increasing thickness may be not efficient because your moment arm is almost identical, but you're increasing the flange thickness. So we better think about other more efficient way to increase the stiffness, which we're going to consider some outlier later on. So this is the first step. Whatever your default wall thickness, if you're using 12-inch thickness, you maybe end up with a pretty significant deflection in one weak axis, right? So what we're gonna do is now we are basically increasing the we need to find the lateral stiffness, which is we are talking about moment of inertia and Young modulus. Here I create the table, right? We maybe create the more materials properties based upon the concrete strength. I think default, I think ETABS has a 4000, but would like to use more high strength concrete. Also, wall thickness, we're gonna just, I think we have currently 12 inches, but we may be using a thicker wall. So we're gonna define these properties like this. So concrete strengths, maybe we can just have some kind of the material names and the wall thickness name and beam name. So kind of use their thickness and concrete strengths, width and depth, so that we can easily kind of control our all member, our ETABS model. So let's go to the ETABS and we're gonna unlock. So this model is the original model. I want you to keep it. And the second model, I want you to add, create the version 1. And I'm gonna, first of all, create the material, right? So additional material, but our default is 4000. So you could see the 4000 material properties right there. Most likely we're gonna change the Young modulus based upon concrete strength. What we're gonna do is maybe we're gonna copy, right? The 5000 concrete. I'm gonna just use C5, simple, short. So Young modulus, either we can type it or there's an internal calculators. So I'm gonna just type the asterisk and SQRT because Young modulus is proportional to the square root, right? So 5 divided by 4. So ETABS can calculate the Young modulus. Basically, so we're gonna calculate either we can fill in this Young modulus or just use the formula based upon the proportion, right? So I'm gonna ratio. So I'm gonna create another few more material properties. Now 6000 SQRT. I'm gonna type C divided by 6 divided by 5. Now I'm gonna use a 6 to copy C7. 7 divided by 6. Okay, calculate that. I'm gonna create C8. C8. Now we're gonna create C9. 9 divided by 8. Okay, so I created, let's change these names. C4. Alright, so we create all very more concrete strengths properties. Now let's create the wall thickness, right? Default has probably this default. Okay, default I think this model has default C24 4000, but I'm gonna use this one maybe 9000, right? 24 inches, C9 concrete strength. So I'm gonna continue similarly. I'm gonna copy, right? W C22 C8, right? So 22 C8. So oh, I don't have C8. Oh, yes. Oh, okay. I'm gonna use 7 then. 22 C7. Okay, I'm gonna copy W20 C6 12 C6 6 20 C6. I'm gonna copy one more. So W18 C5 C5 18. Alright. So for now, I'm gonna set it up this wall. I'm gonna save it. I think it's also typically because a concrete core wall is made out of wall, and this coupling beam, because it is part of concrete construction, right? So we're using this tie beams is as a concrete beam. So we're gonna define the concrete beam as well. Okay, let's see. We have some. Okay, let's change this one. So this beam, especially we call it a link beam. So we have 18-inch thick wall, right? Depths, we're gonna just assume all 24 inches. And concrete strength at the top, like wall thickness 18, we're using C5. So I'm gonna use a C5, right? So width is 18, depth is 24, right? Okay. Again, I'm gonna just copy and change the name 20 by 24 C6 C6 20 by 24, right? And then copy a few more. So basically, we have to define the material property, section property, and material property. But once you create this, you maybe create the template, so you don't need to recreate every time. Okay, so the last one, I'm gonna change the property 24 by 20, 24 by 24, whatever 9 C9 9000 concrete. I'm gonna use this. And this beam might be a little bit, let's keep save it. So what we're gonna do, so we need to assign that properties to various the wall. So what I'm gonna do, I'm gonna just turn off the all. I'm gonna put this in 3D, and basically I'm gonna put 3D and XY plane aperture 0, so everything is on 3D. So I'm gonna just select, before I select, I'm gonna change this one to section property so I can see the color. So let's say bottom floor, I'm gonna assign shell wall thickness. At the lower, I'm gonna use a thicker 24. And I'm just roughly change 22 at the middle height. And let's see. And then 20 upper zone. Oh, I need to change the color. Probably everything default. Okay. So I just assigned the properties, but seems like I have same color. 18, so I have a cyan color. Okay. 20, let me change to 22 default color. Okay, let me refresh. Okay, so I changed the wall thickness along the height, right? Now I have to do the same thing, the wall, the beams, coupling beam. Maybe in order to select only concrete beam, and maybe try now everything. I put this one. Oh, I have to turn on the beam. Turn on the beam. right? And put everything in 3D XY plane. So question is I need to project down all so I can select entirely and show the only member. Then I'm just selecting all column, oh, wall and concrete beam together. So basically none of steel beam I don't want to select because I don't want to ruin it, right? Those are all wall, concrete wall, which we already assigned. Now we try to assign the concrete beam property. So this is how I select. I'm gonna put XZ plane in 0. So okay, now in 3D everything I can select like that. So I select the floor below all the beam and go to assign frame, section properties. Basically I'm gonna select the beam as 24 inches as thick as the wall thickness. So I just assign 24 by 24 right there. And then approach on, I'm going to select and assign 22 by 24, which is matching, and also 20 and 18. So wall thickness and the beam width is same, matching, right? So I think this is just quickly I assign randomly the wall thickness and associate wall concrete strength. So let's run it. So basically, we try to thicken up. Oh, wait a minute. We may end up with more higher deflection. I think it's probably previous model we have 24-inch wall all the way up. Let's see what we'll get. So the procedure is we need to define the section properties and material properties, and then each section and associated concrete strength we assigned to our wall along the height, right? So let's check this model and deflection, and due to the wind Y, and see what we get. Oh, 21 inches. You see that? So it used to be a 26. Now it went down to 21.4. Basically, we assigned the wall 24 to 18, but with the various concrete strengths, right? So this is kind of one step. Let's say we're gonna click all the data, the deflection in Y directions, Control C, and this one previous Excel data. So we added. So you see the 26 to it went down to 20. So this is second model, right? So we need to continuously do this. This is also workflow until we meet. This is what h over 400, which is 600 feet times 12 divided by 400. So we're gonna continue to do until we meet at the top 18 inches. But since this wall is already thick, we maybe think about better, more efficient the way to increase the lateral stiffness instead of just keep increasing the wall thickness is more material and it's not efficient because eventually increase the foundation wall reaction. So this is iteration. I want you to just aware and then also prepare some document which is table, right? So Excel always like the number. So I'm gonna use the floor story, and I'm gonna add the chart. Select data, add. First, X is deflection, Y here, and Y is story, right? So this is first of all, maybe you want to say version 0. Now 1 is version 1, we increase the word thickness, right? 24 to 18, and also concrete strength. So basically, you can show your improvements, right, along this system. Chart title, axis title, data, legends. Okay, legends, right? So this one is lateral deflections and Y under service when Y direction. This is story, right? This is deflection. So inches. So this is kind of one of example you guys should to learn and organize your own data, how to present your current study so that your supervisor will understand. So meanwhile, this model is we call version 1. It varies thickness 24 to 18 inches, right? And concrete strength C9 to C5. First model we better check what did we use, but I think you need to just list it what you've been changed and understand what is structurally efficient. Okay, so all right, so this is the end of the today's class. I think you guys actually working on this Tuesday and next week, so we try to finish the at least the size. But the component, I think I'm gonna explain during the class and then also in the next following the video, which we're gonna add the outrigger in the weak axis. All right. Okay. I hope you guys can finish this at least this coming Tuesday, and then we're gonna move on. All right. Okay. See you.